For today's colloquium, we're pleased to have Professor Lizhen G from our enemies up north, the University of Michigan. And I've known him for quite a long time. I think, I'm not sure I can really go through his, I didn't look up his credentials, but I think he's, I mean, his awards and things, but he's, I think he he was a student of Yao and maybe Goretzky, and he's one of the big experts on compactifications of locally symmetric spaces and maybe of moduli spaces. So I think, and I think that's related to what he's going to talk about today, which is the geometric Schottky problem. Okay, Lizhen.
Okay, yeah, thank you. Thank you very much for the invitation, for a chance to give a colloquium by Zoom. Well, this is a new format or way of living now. Okay, so here's my plan. I'll set up the Schottky problem. Then I'll talk about motivation and the history of the Schottky problem. In preparing for this talk, I spent quite some time to search out the history and motivation. And this is quite amazing. And for me, I found several surprising things. I hope you will learn something new from this history part too. It's quite interesting. There are many things we deal with every day without thinking about why people did that. Okay, I'll show them later. Then third part, I'll talk about geometric version of the Schottky problem. Then last part, I'll talk about some results. Okay. So I started with definition. So a Riemann surface is a one-dimensional, complex manifold. So this notion was introduced by Riemann in his thesis in 1854, foundation for general theory of function of one complex variable. I wonder how many of you have actually read, open and read Riemann's thesis. This is quite amazing. If you have never tried before, I encourage you to take a look. Okay, so one question he addressed in this thesis is, what's the natural and the maximal domain or definition of a holomorphic function under analytic continuation? The answer is Riemann surface. So for every germ of holomorphic function, we get a holomorphic function. Okay, another major result of the thesis is the Riemann mapping theorem. So it's not a bad thesis. Okay. Now, under analytic continuation, we often get a multivariate analytic functions, but the use of Riemann surfaces as a domain make them single-valued. Okay. So in this talk, I will concentrate on compact Riemann surfaces. So they are classified topologically by the genus, the number of handles. So here's one picture for genus 2. So I'll denote a compact Riemann surface genus G by SG. Okay, so that's a compact Riemann surface. Now, so Riemann's thesis was 1854. 3 years later, he wrote this very famous paper, Theory of Abelian Functions. So Riemann used the Riemann surfaces, in particular, the topology of Riemann surfaces, to study abelian integrals. Abelian integrals are integral of, here R is a rational function, Z and W. W is algebraic function of Z. So Z and W related by a polynomial. Such integral is called abelian integral. Well, Abel studied this, so it's named after Abel. Okay. Now, 1P is a reducible polynomial that is a canonical connected compact Riemann surfaces associated with the plane algebraic curve. The polynomial defines the algebraic curve. So from this algebraic curve, we can construct a canonical compact Riemann surfaces by desingularization and compactification. What's the advantage? Once we have the Riemann surface, the integrand, we become a meromorphic differential form on the Riemann surface. So this solved a major difficulty problem facing Gauss, Abel, and Jacobi, that the integrand and elliptic integrals are multivalued. But now, once you introduce the Riemann surface, it's a single valued. And more importantly, this also gives a topological interpretation of the number of periods and elliptic integrals. It was a major thing. Okay, so this will become relevant in a minute. Now, Riemann's paper is very rich. It contains many things. One particular thing is he introduced the notion of modular space. Modular space Mg, or compact Riemann surface of genus G. So was first defined here. So Mg is a set of the biholomorphic equivalent classes of compact Riemann surfaces, where two Riemann surfaces are equivalent if there is a biholomorphic map between them. So this probably is the most important modular space in mathematics. One of the most important one. Now, there is another very important modular space, AG, of abelian varieties of dimension G with the principal polarization. So here's the definition of this abelian variety. You see, we consider compact complex torus of dimension G is the CG over lattice. L is the lattice of the same G. So this is the compact complex torus. Now, this torus is called abelian variety if this can be embedded into projective space, i.e., when the complex torus is abelian variety, is an algebraic variety, we call this abelian variety. Okay, so that's the definition of abelian variety. Now, unlike the case of G equal to 1, in dimension 1, not every complex torus is a projective variety. You see, in dimension b equal to 2, it's not true. So that's why the condition being a projective variety picks out some special compact complex torus. Okay. So here's a condition. When can this happen? This was due to Riemann. Okay, so a complex torus can be embedded into projective space if there is a polarization or ample line bundle on this. So what is a polarization? A polarization on a complex torus is a positive definite Hermitian form on CG whose imaginary part is integral on the lattice. Okay, that's a polarization. And what do we mean? The polarization is the principle if the determinant of this imaginary part, the integral skew symmetry form, is equal to 1. So that's a principle, that's a polarization, that's a complex torus. This gives abelian variety. Okay, so this AG, of course, is very important. MG is very important. Since both are important, it's not surprising that is a very important map MG to AG. This is called the Jacobian map or the period map. So I'll give a quick definition here of this period map. So H0 SG omega 0, that's the space of holomorphic one forms on SG. Okay, so this is a complex vector space of dimension G. That is embedding of the first homology. This is Z2G embedded into CG, the dual space. So what's a map? Whenever I have, so how does one cycle, which define a linear function on this holomorphic form by integration? Given a cycle here, given a holomorphic form here, so the value is given by the integral of the one form on the cycle. This turns out to be embedding. So this is a complex vector space CG. Here we have lattice. So the quotient is a complex torus. It turns out this is a natural principal polarization. So we get, that's the Jacobian, the variety. So that's the map. I map every Riemann surface to it's a Jacobian variety, which is an abelian variety with a principal polarization. Now, one important problem to understand this map from MG to AG. Here's the first basic result. It's a Totality Theorem. The map is injective. So MG is a map injected into AG. But it cannot be a surjective. 1G bigger equal than 1G is bigger than or bigger equal than 4. Okay. So that's typo. Bigger than 4. The reason is the dimension of MG is 3G minus 3, And dimension of AG is G times G plus 1 over 2. You can compute when G equal to 4. So this is 9, here is 10. In fact, in this paper of Riemann 1857, Riemann, he probably assumed that MG is a complex space. Well, he did not say anything. He counted the number of essential complex parameters needed to specify a point MG. And this number is 3G minus 3 when the genus is bigger than 1. And he called these numbers moduli. Because of this, people call MG the modular space. Okay. The dimension of AG, I'll explain this in a minute. So the question is, since MG is very natural, AG is natural, this natural map, what's the image of J or MG? So that's a basic problem I want to discuss. Now, before that, let me mention Riemann's modular problem. Right? Riemann probably assumed MG is a complex space of dimension 3G minus 3. This becomes Riemann's modular problem. So this was first solved by Teichmüller. MG is a complex orbifold in 1940s. Later on, Mumford, he showed MG is algebraic variety. Now, so that was finished, proved in the 60s. Also around the 60s, AG is also algebraic variety. Okay, let me explain how AG was proved to be algebraic variety. To show its algebraic variety, I'll start with the Ziegler upper space. So X plus IY, both X and Y are G by G real symmetric matrices. Y is positive. So this is the Ziegler half space of dimension or degree G. This is a Hermitian symmetric space. The symplectic group acts holomorphically and transitively on this. Therefore, Ziegler upper space can be written as a quotient SP over UG. Now, the Ziegler modular group SG 2GZ, a lattice in the symplectic group or arithmetic group, acts properly on the Ziegler upper space, and the quotient is a locally symmetric space. It turns out that is a canonical identification of AG with the quotient of Ziegler upper space under the action of symplectic group SP2GZ. Therefore, this is called the Ziegler modular variety. Due to the following reason, every abelian varieties with principal polarization can be written in this form: CG over this lattice. This lattice is rather special. ZG times, this is a point in the Ziegler upper space, X plus IY times ZG. This is a lattice in CG. So therefore, each point in the Ziegler upper space will determine a lattice. Now, some different choices will lead to the same isomorphic abelian varieties. That's why we go to the quotient by SP2GZ. But in any case, this shows the dimension of this is the dimension of the Ziegler upper space. That's G times G plus 1 over 2. This is a crucial number. This will appear again and again later on. Now, Schottky Bailey showed that this locally symmetric space admits a natural compactification as a projective variety in 1960s. Therefore, since we have the identification of AG with this locally symmetric space, therefore AG is a quasi-projective algebraic variety. So this is the beginning of the Bailey-Borel compactification of locally symmetric Hermitian symmetric space. That's the first example. The Bailey-Borel was motivated by this. Okay, so this is the proof AG is algebraic variety. Now Bailey also proved another thing. The image is algebraic subvariety of AG, because earlier we only have a map. Therefore, this is a proper subvariety when G is bigger than 3. When G equal to 4, MG has a dimension 9, AG has a dimension 10. Here's a Schottky problem from 1888. Now determine the defining equation for this subvariety or characterize the Jacobian among all abelian varieties with principal polarization. You say AG consists of abelian varieties. JMG consists the Jacobian. So what's special about this Jacobian? You see, based on what I said, this JMG is a very natural subvariety. It's not a random subvariety. So determining or characterizing a natural subvariety is a natural problem, right? So based on my logic, the Schottky problem is a natural problem. I hope you are convinced by that it's a natural problem. But something's wrong. Take a look at this picture. Do you see something's wrong? Schottky died in 1935. Mumford was born in 1937, Schottky 1929, and Bailey 1930. Basically, all the people were born after Schottky was dead. So Schottky, he did not have this result on algebraic varieties. So probably he was not interested, motivated by the problem to determine a natural subvariety, JMG. Right, this cannot be right. Question, what was his motivation? Now, since the Schottky problem was a major problem in algebraic geometry, probably still is. So I want to know what is its history. It turns out to be very long, very, very interesting. So next, I'm going to show you what I found. So besides the Schottky, the Jacobi, Riemann, Weiss, Charles, Poincaré, they all worried or thought about this. Okay, so there was some interesting story we come out of this. So I started with Jacobi. Okay, Legenda spent several decades to work on elliptic integrals, and he wrote multiple books, at least 5 volumes, and plus some papers. But he only dealt with real numbers and never thought of inverting them to obtain and study elliptic functions. Never extend to the complex. Then Abel and Jacobi came with 2 crucial ideas: extend the variable to complex numbers and invert the elliptic integral, similar to consider, you see, to consider y as a sine x instead of study x as arcsine, because arcsine is much harder to study. So that was the point of view of Abel and Jacobi. Gauss, of course, had a similar idea, but he only wrote down in his diary and never published them. Abel and Jacobi was awarded the grand prize by the Paris Academy in 1930. If you remember this, if you remember this picture, oh, no picture, okay. So Abel died in 1829, but the prize was given in 1930. As some of you know, because the Paris Academy felt so bad because they messed it up. So that's why they want to give Abel a prize to show their regret and appreciation for this work. So this is Abel Jacobi. 3 people. Now, even though Gauss, Abel, Jacobi, they all introduced complex variables, it was more formal. They could not handle integral or complex function and pass integral. One issue is the integrand are not well defined, multivariate. I mean, that's the problem. So what they do, they don't really use the complex integrals we are familiar with. They use the theta functions and express elliptic functions as quotient of the theta function. So they avoid integral. Now, since the theta functions are closely related to problems in arithmetic number theory, so they were emphasized by Jacobi, and also it was developed by others substantially. So theta function very useful. Now, elliptic integrals were associated with a polynomial equation of degree 3. So W squared equal to PZ. P has a degree 3 or 4. This is the integral rational function Z square root of PZ dZ. So this gives rise to the elliptic integral. If you look at this, it's very natural is, why do you insist the degree P to be equal to 3 and 4? You should allow a higher degree. So this gives rise to so-called hyper elliptic integrals, right? So Abel and Jacobi consider hyper elliptic integrals and even more general abelian integrals I start with. So R, ZW related by polynomial equations. Okay, but okay, now so they had a competition between Abel and Jacobi. Since Abel died very young, so the competition ended very soon. The field was open to Jacobi. Okay, Jacobi, a big problem for Jacobi is how to invert abelian integrals as in the elliptic case. This is the Jacobi inversion problem. You see, the earlier for elliptic integral, you just inverted the function. It's rather simple, though it's not easy to study it properly. But for the hyperelliptic integral or general abelian integral, the inversion cannot work. The reason is it has too many periods. In genus equal to G, you have 2n, 2G independent periods. A function of one variable cannot have 2G periods when G is bigger than 1, unless your function is constant. So that's the problem. Okay. So it's not easy how to do the inversion right away. That's why the next case, when genus equal to 2. And it was a difficult problem. So Paris Academy set this as a prize, and this was solved by these two people. So that 2 is still theta function, and elliptic functions are replaced by abelian function in 2 variables. So minimum function on C2 is 4 independent period. Okay, so second person received the prize, but the first person, he did not submit the prize. Now after this, the Gopal was very optimistic. He thought his method should still work for hyperelliptic integrals of higher degree. And the quotient of theta function should give abelian functions on CG with a 2G period. That's what he thought, but Jacobi did not agree. His reason is this: the modular space of hyperelliptic Riemann surfaces of genus G has a dimension 2G minus 1, while the theta function in G variables are parameterized by the Ziegler Abel space HG, because it's positive definite matrices. You see, when G equal to 3, 2G minus 1 equal to 5, less than 6, which is G times G over 2. So there are more theta functions than those coming from hyperelliptic Riemann surfaces. So that's a problem. So you have some abelian functions which don't come from hyperelliptic integrals. Okay, so here's the problem: how to characterize theta functions coming from Riemann surfaces. So that's the Schottky problem before Schottky. Okay, that's Jacobi. Weierstrass. We all know Weierstrass, right? When I was a student, I heard about this. Weierstrass moved from a high school teacher to a university professor at age of 40. Have you ever wondered what happened? And what did he do? Well, based on which paper, which result, he changed from high school teacher to a professor in Berlin. That's a huge jump. Okay, how many of you know the answer? Well, it's difficult to see you guys. Okay. And which paper? It must be an important paper. Weierstrass solved the Jacobian inversion problem for general hyperelliptic integrals in this paper, 1854. It was a major result. This was his first paper published in a major journal and made him very famous overnight. But in this paper, he also claimed a solution to the about Schottky problem of how to determine theta functions coming from hyperelliptic Riemann surfaces. Okay, so let me quote what he wrote here in this paper. He said Jacobi had already observed for n equal to 3, the generalized theta functions contain more constant than the abelian functions of 3 variables. Therefore, determining relation must hold among these constant in order that the relevant series lead to abelian function. So he claimed a solution of the Schottky problem for genus equal to 3. Right? He claimed a relation for hot abelian integrals, but he did not give any detail. He just stated in the paper, okay, I have the proof. But 2 years later, when he published a more detailed expanded version of this paper. This is a much longer paper. You see here is, well, it's like 20 some pages. This almost 100 page, even a part of that. Well, I did not mention this problem anymore. No result or anything related to what I said about the relation which you determine an abelian function coming from hyperelliptic integral. But this problem, this bothered him for the rest of his life. How? So here's another question. So I'm teaching real analysis, a serious calculus this semester. We use an epsilon delta definition, uniform convergence, Weierstrass M test. I'm sure all of you have learned that and studied that. Have you ever wondered why did Weierstrass do that? Why? Now, Weierstrass' life dream was to develop a theory of abelian functions, in particular those obtained from the inversion of abelian integral. That's his life dream. Okay, let me quote two things to support my statement. After Weierstrass died, Poincaré wrote an overview of the mathematical work of Weierstrass. That's what Poincaré wrote. Right from start, Weierstrass set himself a definite goal, and then he created methods to achieve it. Sometimes he tried this method on other problems, but he never loses sight of the final object of his research. He had ambition to create a complete and coherent theory of abelian functions. That was his life dream. Can you guess what happened? Well, he did not achieve it. He claimed he did, but he did not achieve it. The reason he did not achieve this theory till the end of his life was explained by Milton Leffler. Milton Leffler was a student of Weierstrass, very close one. He said Weierstrass wanted to derive the properties of the most general abelian function from three different points of view. One is the addition theorem. As you know, for elliptic integrals, the first breakthrough is addition formula due to Euler. So for abelian function, it's similar. Addition problem theorem is important. Another is elliptic functions are periodic. Abelian function also periodic. The third one is from the theory of algebraic differential equation. Solving differential equation is like integral. So this is from abelian integral. Weierstrass wanted to have a theory of abelian functions from three perspectives, but he met a difficulty. Now, the dimension of algebraic curves of genus G is 3G minus 3. That's a dimensional modular space. Where else the number of arbitrary constant or possibly relevant theta function in G variable is G times G plus 1 over 2. That's the dimension of the Jacobi space. So the same problem again, 3G minus 3 is less than G times G plus 1 over 2. Schottky problem. What could come in place of the differential equations? Is we don't have 3G minus 3 is smaller than this G times G plus 1 over 2. It's less. So that's this bothered him. Weierstrass struggled almost all his life with this question. So this bothered him. Yeah. So that's the short. That's exactly the Schottky problem. So this prevent the complete realization of Weierstrass, the whole dream. He developed all this epsilon delta definition, absolute convergence, M-test, everything in order to develop a theory of abelian function. But he could not do it. He did not achieve it. Yeah, so it's a sad ending. Riemann. Next person was Riemann, I mentioned earlier. So he solved the Jacobian inversion problem for all abelian integrals for all compact Riemann surfaces using theta function in this paper, Theory of Abelian Functions. And now, if you remember the title of Weierstrass paper, you realize almost the same title as Weierstrass paper. I guess Riemann chose the same title on purpose. Okay. Now this paper contains mg, and Riemann law theorem is also here. I mean, when people take a course of Riemann surfaces, Riemann law is a basic theorem. It's also here. But the main theorem is the Jacobi inversion for all abelian integrals. So this paper is his most important and famous paper in his lifetime. That's how he got the chair of Gauss in Göttingen. Much more famous than papers of Riemann hypothesis or differential geometry people know now. Okay. Now, this very famous paper has a devastating effect to Weierstrass. Weierstrass was expanding his first paper, but he published one long paper already. He was writing another to expand other parts of this paper. Weierstrass was proofreading his paper, but when he saw this paper, Riemann, he withdrew his paper. Right. So he withdrew a sequel of this long paper. These two papers will give a detailed treatment of his earlier paper of hyper-Euclidean integral. Right. This is the first paper made Weierstrass very famous. This is the expansion part of this paper. Then he wanted to expand more. But when he saw this paper of Riemann, he withdrew it. About 1.5 years later, Weierstrass had a nervous breakdown. Then after recovery, Weierstrass often challenged Riemann's work. For example, Riemann's use of the deletion principle. Now, of course, after Riemann's death, the computation was over, yeah. Now, in Riemann's work, he also needed some special property of theta function coming from abelian integrals. He also realized this problem, 3g minus 3, which is less than g times g plus 1 over 2, when g is bigger than 3. So more theta functions than those coming from abelian functions. So this is a natural problem on Riemann. But Riemann did not publish anything related to the short problem. On the other hand, in some unpublished lecture notes taken by various people, Riemann did some computation which looks very similar to what Schottky did later, claiming that there exists so many relations of this difference. Then Schottky appeared. Schottky, in this paper in 1888, he started case G equal to 4. So modular space Mg is dimension 9, Ag dimension 10. So he gave one algebraic relation among theta constant, which cut out the Jacobian locus. Later on, in another paper, he formulated the Schottky problem I mentioned in the beginning. Okay. Now, Schottky was a student of Weierstrass, so it might be interesting to see a comment of Weierstrass on him. So he said that Schottky is a sensible, somewhat dreamy person who sometimes is able to find the right idea only by instinct. He said, I cannot prove it, however, it's right. It's a usual way of speaking. So I guess this is a good comment on the Schottky problem too. Poincaré, okay. Now, earlier I have mentioned several paths about Jacobi, Riemann, Weierstrass. They all compete with each other, right? About Jacobi and Weierstrass, I mean, Riemann is made Weierstrass quite upset. So here, since I mentioned Poincaré, I also want to mention another path, Hilbert. Well, you may wonder whether they compete for something, since they do not work on similar problem. So what do they compete? Yes, they do compete. So they were the top 2 mathematicians in the world at that time, but have different perspective about mathematics. So they want to show that difference and promote their own. So here, Poincaré gave a plenary talk at the first ICM in 1897 in Zurich about interaction between math and physics. And in the second ICM in 1900 in Paris, Hilbert wanted to challenge Poincaré's perspective. He wanted to concentrate on problem inside pure math. So he made a famous list of 23 problems for the future of mathematics. So this is well known. So everyone knows about this. But the next one may not be so well known. So next ICM was held in 1904 in Heidelberg. And Poincaré was not there. Actually, he was in USA. In 1908 at ICM in Rome, Poincaré, he gave a plenary talk with the title Future of Mathematics. He wanted to challenge Hilbert's point of view. He proposed a list of 10 open problems to counterbalance Hilbert's list. So if you have never looked at Poincaré's list, it'll be fun to compare them. And each has a long introduction about the mathematics and what is important about the mathematics. So they are quite interesting to read. Why do I mention this? Because number 6, number 5 on Poincaré's list is this. He said, one knows the principal question that remains to be resolved in the theory of abelian function. The abelian functions, which come from algebraic curves, are not the most general. There are only a particular case that we are called the special abelian varieties. Okay, so these are come by Riemann surfaces, as I mentioned. How are they related to the general one? And how can we classify the latter one? So I can reformulate Poincaré's question in two. First, we need to determine the image of JMG-NAG. So this is the Schottky problem. And the second, to understand the AG and the related function theory. So this is quite a modern formulation of the Schottky problem. JMG-AG. Okay, so this is a concern by all these historical figures. Now let's go back to the more recent time. So there has been a lot of work on the Schottky problem by various approaches. Novikov formulated one conjecture how to characterize the Jacobian varieties in terms of the Riemann theta function by differential equations. So basically here is a conjecture. Abelian variety is a Jacobian if and only if its Riemann theta function satisfies a nonlinear differential equation, a KP equation. So this was solved by Shioda in 1986. Okay. So this is one solution of the Schottky problem. Now, so I go to the geometric Schottky problem. So as I mentioned before, AG is a quotient of the Ziegler-Abel space by SB to GZ. Ziegler-Abel space is a Hermitian symmetric space of non-compact type. Therefore, it carries a complete invariant Riemannian metric of non-positive curvature. So since this metric is invariant under the whole Lie group, it's also invariant under this lattice. So it descends down to a complete metric on AG. Therefore, AG is a locally symmetric space of finite volume. So earlier we emphasized AG is algebraic variety. Now we want to emphasize AG is a locally symmetric space of finite volume. Now, since AG is a locally symmetric space, JMG is a subspace. One natural question is to understand this subspace as a metric subspace, right? So we can consider properties of the induced metric or distance on this subspace, right? So this is the general question of the metric geometric Schottky problem. We want to emphasize from the metric perspective, how is this subspace? You see, we can ask many questions. For example, the location of this subspace inside this metric space. Since we are dealing with the metric space, we want to understand its shape. We also want to understand the size. So I'll ask more precise question later. You see, since AG is a locally symmetric space, so this geometric Schottky problem seems natural, but you may See, it's still artificial, right? Why do I care about this? Okay, I have a locally symmetric space. You have a subspace inside. Why should I care about this symmetric subspace? But there are some more practical reasons. So let me give you one reason. As I mentioned before, when G is bigger or equal than 4, the GMG, the image of the modular space, is a subvariety of AG, of positive codimension. Since it's subvariety of positive codimension, the probability, if you pick any point, the probability that the V lies in this, this should be MG. Inside this JMG is 0, right? So you have 0 probability, you're gonna hit a subvariety. But sometimes we want absolute certainty. So the question is, give a concrete abelian variety, which is not JSG, which is not a Jacobi, right? So pick a point in AG, which is outside this subspace, right? So that's a very fair question. How do I find a abelian variety which is not a Jacobian? Well, so you said it's easy, right? We just apply the solution of the Schottky problem by the Novikov conjecture by Shioda, but this solution is not practical. Suppose I give you a abelian variety. How do I check its Riemann theta function satisfy a nonlinear PDE? It's almost impossible in practice. So we cannot do it, right? It looks impossible in reality. So what can we do? Looks difficult. Then in 1994, Booth and Sonic had a geometric perspective. Well, he said AG is a complete metric space. They define the notion of distance to the infinity. Well, this must be normalized since the complete space, the distance to infinity is over the infinity. And they show that the Jacobian locus is contained in an expressed tubular neighborhood, small neighborhood of the boundary. I denote this neighborhood by n epsilon. So let me show you on the whiteboard. Okay, so this is like my AG. A better picture, AG here. So here I have a tubular neighborhood near infinity and epsilon. So this is J MG is contained in this. So this is the result. So we have a small neighborhood, tubular neighborhood near infinity, which contains the image. Okay, I'll go back to here. Right. So this is the Jacobian locus is contained in this small neighborhood. Actually, so they do a computation. This small neighborhood has a very small volume. As G goes to infinity, the volume of this small neighborhood over the total volume of this locally symmetric space is of exponential decay. One important is their neighborhood is very explicit. So what they do, how to find the point, abelian variety, which is not Jacobian, they just pick a point. Explicit point outside this neighborhood, so it's done. So this, you see, so this geometric perspective is very helpful, allows you to pick an explicit abelian variety, which is not a Jacobian. Let me also mention another reason for the metric consideration. If TG is a Teichmüller space, then which is a modular space of marked Riemann surfaces. And MODG is a mapping class group of the surface. Then MG is a quotient of the Touch-Miller space under the mapping class group. So that's how Touch-Miller proved MG is a complex object flow. Now, a lot of work has been done to show the Touch-Miller space is different but similar to a symmetric space of non-compact type. And the mapping class group is similar but different from the arithmetic lattices and semi-simple Lie group. So they are similar but different. Since AG is a locally symmetric space and MG is not a locally symmetric space, so it's natural to expect that the image is not a locally symmetric space AG. Well, that's very natural. In fact, it's expected that the image, it does not contain any non-trivial special locally symmetric spaces. Now, let me mention two quite known conjectures in arithmetic geometry related to AG and MG. One is a Coleman-Alt conjecture, another is Alt-Andrews conjecture. Let me state them very briefly. Points of AG are Abelian varieties. There are some special points which actual symmetry are called the complex multiplication. These are so-called CM point, complex multiplication points. And they are generalization of elliptic curves with complex multiplication. So the Coleman-Alt conjecture said when G is bigger or equal than 1, the image, the Jacobian locus, contains only finite many CM points. Okay, so they don't hate these special points too much. And all the conjectures are only special locally symmetric spaces inside AG will contain many CM points, Zariski dense point. If a subvariety contains dense Zariski dense CM point, then this subvariety is very special. It's a locally symmetric space. So the image is not such a special one. Now, Benson Fabre, after seeing the result of Busse and Sarnak, he raised this Cauchy-Schottky problem. So how dense is the Jacobian locus inside AG in the sense of large-scale geometry of AG, in large-scale geometry of Gromov? Okay. More precisely, AG is a complete non-compact metric space. So it has a tangent cone at infinity, T infinity AGD, where D is the metric on AG. Cauchy-Schottky problem is to determine the image of this, the Jacobian locus inside the cone at infinity. So that's the Benson Fabre, the Cauchy-Schottky problem. Okay, so here's the definition of the tangent cone at infinity. So I have a metric space. How do I define the tangent cone at infinity? I scale down the metric by epsilon. I look at the limit of this sequence of metric space with the chosen base point as epsilon go to 0. When you scale down the metric space, how does the metric space look like? Right. So this is a sort of similar to Busse-Sarnak's perspective in terms of metric of AG. So in joint work, we proved that the image is coarsely dense in this AG. So this means there exists a constant CG such that for every point in AG, there exists a point in the image such that the distance is less than this fixed constant. So in particular, the image is mapped onto the whole cone. Okay, so this solves the Cauchy-Schottky problem. Now, at first, this may sound surprising because Busse-Sarnak says JMG is containing a small neighborhood of the infinity, but we say JMG is almost dense. There's no contradiction because the constant CG here goes to infinity. Let me go to the next problem. Now, as mentioned earlier, JMG is not a locally symmetric space inside the AG. So this should not be a totally geodesic subspace. So it should not be like a locally symmetric space. Now, in general, suppose XD is a path-connected metric space, Y is a path-connected subspace. Then we have two induced metric on Y. Y is just a restriction D to Y, I still denoted by D. Another induced length metric on Y, I denoted by D prime. So how this is defined? For the length metric on Y, for any 2 point PQ in Y, I consider all passes which connect P to Q, right? A pass in Y, start from P, go to Q. Then the length is the nth of the length of all these passes. Okay, so that's the induced length metric on the subspace. Now, clearly, the induced length is bigger or equal than the restriction of the metric, right? So let me just show you one familiar example here. Suppose I have a circle inside, so this is my Y. That's inside R2 with Euclidean metric, you see? So the restricted distance is this here. So this is the D here. But if I compute the length here, so this will be longer, right? So that's why the induced length is bigger or equal than the restriction. So the ratio of the induced length of this measures the metric distortion of the subspace inside. Benson further raises another question. It's a distortion problem. Now determine the distortion function of JMG inside AGD. So he said that it should be very wild and maybe exponential. Okay. So what's the distortion function here? Given such a space, is a D prime is a function of D, you see. So F prime measures how distorted the subspace is inside. Now this notion came up particularly in geometric groups here theory. So if G a finite geometric group, as a finite geometric set, we have a world metric. So if we want to deal with only the path connected space, look at the Kitty graph. So I get a connected metric space, path connected metric space. If G prime is subgroup, the S prime is generally in the set. So let's assume S prime contains S by enlarging S necessarily. Then we have such a map inside here. Now clearly, the world metric for S is less equal than the world metric for S prime, since I have more choices here. Now the metric distortion function is F. This should be the almost equal. So ds prime is almost equal to f of ds. So this is the distortion. Now this distortion in this case is at the most exponential. So that's why Faber said maybe the Jacobian has the worst distortion. Okay, so what's the result? So here's one result. Now this map, mg into ag, or the subspace is a folding. What does it mean? So that's a positive constant and two sequence points in the image such that that distance goes to 0, but the length matrix is positive. You see, the ratio goes to infinity. So here, as I said, so this ratio measures the distortion. So in this case, the ratio goes to infinity. So there is no distortion function. Okay, so let me show you some pictures of several kinds of distortion. So I want to show R map to R2. First one, of course, I map this into line here, right? Second one is, so I look at this. So this graph is so this embedding x equal to y squared. So this has a polynomial distortion. Now the third one is this. So I take a log y equal to log 1 plus x. So this has exponential distortion. What is a folding? Folding is like this. You see, I have point here, P and Q. P here and Q here. You see, in the induced distance is very short, but if you move along the length, this is quite long. So this is a folding. Let me go back. Okay. So this is the picture I want to show. This is a folding. Yes, it's a wave, you see. So that's how MG looks like inside AG, you see. You have this point are very close, but if you go back, but the induced length distance is not short. That's it. I think I'll just stop here. Yeah. Hello?
Okay. Thanks a lot, Lizhen. That was a great talk. Maybe we should clap first, and then let's thank Lizhen for his talk, and then see if there's any questions. At least I'm going to thank him for his talk. Okay, are there any questions? Maybe we should, can you unshare your screen maybe? I don't know.
Okay, sure. Okay.
Well, I don't know.
Stop sharing, yes. Yeah.
Well, okay, maybe you have to go back. But okay, is anyone, any questions?
This is Herb Clemens. I had a question. So can you describe in terms of the intrinsic metric geometry of the Riemann surface, where its position is in the fold? Like, is it around
Oh,
the
yes,
hump
yeah.
or out near the end?
Oh, yes. So I constructed explicitly two Riemann surfaces. You see, maybe I should show you the last page. I did not.
Okay, go back, yeah.
So the idea is, you see, I have to construct two sequences of points or Riemann surfaces. You see, both of them lie in the thin part or the attachment space, but the path must go through the thick part. So that's why the induced length is long, even though when we look at AG, they go to each other very closely. AG is very close, but on MG, they have to go through the thick part of the attachment space. So that's how it's proved. You say, I paint along geodesics, those are not conjugate under the mapping class group. Yeah, that's roughly the idea of the proof. Yes, so the proof is very complicated. Somehow I have to choose some points which lie in the cusp of AG, but they have to go through the thick part of attachment space. Okay. Does this answer your question?
Yeah, that helps. I get the idea.
Yes, yes. Actually, for myself, while preparing for this talk, I found all this information about Weierstrass. That's quite surprising to me, actually. I did not realize this problem stopped Weierstrass from realizing his life dream. I did not know he did all this epsilon delta definition for this. And also, I did not know here Poincaré raised this as a problem number 5. Yeah, it's all because of the
First talk.
what?
You're talking about the first talk you gave.
No, second talk. So I said here, Poincaré raised the Schottky problem as a number 5 on his list of 10 problems.
Oh.
Yeah, so that's quite surprising. You see, Hilbert's problem, everyone knows about Hilbert's list of problems, but it seems Poincaré's problem are not so known. I mean, Poincaré published his abridged version of this talk in his book. He deleted most of the problem. He did not discuss mathematics. I think Mumford wrote a paper which discussed some problems, which made people more aware of Poincaré's problem. Yes, so that's it.
Any more questions? I don't have any. Okay, should we thank Lizhen again? Thanks again, Lizhen. I'm going to try
thank you.
clapping. People can clap.